Okay, so in this lecture, we will study the inverse power method. The power method gives us the largest eigenvalue, which is least important in some situation. For example, the mode eigenvector with lowest frequency eigenvalue in vibration analysis. Inverse power method produces smallest eigenvalues. The following facts are the heart of the inverse power method. Number one, if lambda is an eigenvalue of matrix A, then reciprocal of this lambda is an eigenvalue for inverse of the matrix. Number two, the eigenvectors for A and A inverse are the same. So that is the important property, that the eigenvectors for the matrix A and for the inverse of the matrix are the same. We can repeat it. The power method gives us the largest eigenvalue or the dominant eigenvalue, which is least important in some situation. For example, the mode eigenvector with lowest frequency eigenvalue in vibration analysis. Inverse power method produces smallest eigenvalues. The following facts are at the heart of the inverse power method. If lambda is an eigenvalue of matrix A, then 1 over lambda is an eigenvalue for A inverse. The eigenvectors for A and A inverse are the same. Thus, if we apply the power method to A inverse, we will obtain the largest absolute eigenvalue of A inverse, which is exactly the reciprocal of the smallest absolute eigenvalue of A. Again, thus, if we apply the power method to A inverse, we will obtain the largest absolute eigenvalue of A inverse, which is exactly the reciprocal of the smallest absolute eigenvalue of A. So it means we can find smallest eigenvalue of matrix A by applying inverse power method, and just we will take a reciprocal of this value. We will also obtain the corresponding eigenvector, which is an eigenvector for both A inverse and A, matrix A. Here is an example. Find the smallest eigenvalue and its corresponding vector using power method of the matrix. So the matrix is 2, minus 1, 0, minus 1, 2, minus 1, 0, minus 1, and 1. To find the eigenvalue of A that is smallest in magnitude is equivalent to find the dominant eigenvalue of the matrix B is equal to A inverse. Let the initial approximation vector be x naught is equal to 1, 0, 0 transpose, and A inverse is equal to 1, 1, 1, 1, 2, 2, 1, 2, 3 is equal to B. So if we are given a matrix A, we have to take an inverse of this matrix, which we can denote with the B. Then power method gives Bx naught 1, 1, 1, 1, 2, 2, 1, 2, 3. So we will multiply with the initial approximation. So here is a little bit mistake because the initial approximation taken here is 1, 0, 0, but here is 1, 1, 0. So we can verify what is the exact value. So 1, 1, and 1. Uh, I think it is 1 0 0 and 1 1 1 and 1. So this is actually 1 0 0, not 1 1 0. Okay. Because if we multiply with this vector, we have to get the first value as 1 plus 1 equal to 2. But here is 1, it means the eigen vector, this initial eigenvector is 1 0 0. So then we have to take common the highest value which are equal. So we can just write it 1 into. So then we will obtain this x1 is equal to 1 1 transpose this one, and we multiply the next one is bx1 is equal to 1 1 1 1 2 2 1 2 3 and 1 1 1. We multiply again 1 1 and 1, we will get 3 and 1. Okay, so 2 and 2 we will get 5, then 1 plus 2 plus 3 we will get 6, and then again we can take a common value. Here we are actually taking the lower value, not the highest value. So we have to take common as the lowest value. So 3, we will get 1, 1.66 and 12. So then we multiply this value here 1, 1.662 and multiply these two vectors, we will get 4.666, 8.333 and 10.33. We will take a common 4.66 and we will get the vector 1, 1.7857, 2.0, 2142. And then we will multiply again the matrix B with this vector, and we will get the vector 5, 9.01, 11.23. We will take a common 5, so get this vector, and then we multiply this again with the matrix. We will get this 5.05, 9.09, 11.34, and we will take common as 5.05. This is 1.00, 1.80, and 2.24. So we multiply this again with this matrix. So 1, 1.80, 2.24. And we'll get this 5.05, 9.11, 11.36. And we'll get 5.051, 1.8, 2.25. So then we will multiply the matrix with this vector and we will get this one. So just imagine and observe that 5.05 is the same as 5.05. So we can declare this value 5.05. So least eigenvalue is lambda is equal to 1 over 5.05 is equal to 0.1980. So if we want to verify that 0.1980 is the least eigenvalue of the matrix A, then simply we have to find all the eigenvalues of this matrix, and you will get the least eigenvalue of this matrix will be surely this 1 over 5.05, which is 0.1980. Okay. And corresponding eigenvector is this 1.00, 1.80, and 2.25 transpose. Okay. Next is the diagonalization of the matrices. An n cross n matrix A is said to be diagonalizable if it is similar to a diagonal matrix, that is, A is diagonalizable if there exists an invertible matrix P such that P inverse AP is a diagonal matrix. Okay, we can repeat again. N cross N matrix mean a square matrix A is said to be diagonalizable if it is similar to a diagonal matrix. Okay. That is, A is diagonalizable if there exists an invertible matrix P such that P inverse AP is a diagonal matrix. The matrix P is said to be diagonalizable. Diagonalize A. The matrix P is said to diagonalize A. If matrix A is diagonalizable, then it can be factored as A is equal to P diagonalizable diagonal matrix D and P inverse. Where D is the diagonal matrix containing the eigenvalues of A along with the diagonal also written as D is equal to diagonal lambda 1, lambda 2, lambda 3, so on. It means what is the importance of this diagonal matrix is that the diagonal of this diagonal matrix will contain all eigenvalues of the matrix A. Okay, so if we diagonalize matrix A in this way, P diagonal P inverse, we will get all diagonal values on the diagonal of this matrix D. And P is a matrix formed with the corresponding eigenvectors as its columns. And P is a matrix formed with the corresponding eigenvectors as its column. So how we can construct P? We can construct P by eigenvectors. Just taking eigenvectors as column of matrix P. For example, matrices whose eigenvalues are distinct numbers are diagonalizable. Matrices whose eigenvalues are distinct numbers are diagonalizable. Symmetric matrices are also diagonalizable. This property has many important applications. For example, it can be used to simplify algebraic operations involving the matrix A. For example, it can be used to simplify algebraic operations involving the matrix A, such as calculating powers. What kind of this property has many important applications. For example, it can be used to simplify algebraic operations involving the matrix A, such as calculating powers. So, if we have a matrix of order m of power n, so it means we have multiplied matrix A into itself m times. So, this can be written as P dp inverse into P dp inverse into PD inverse, so on m times. And what we will get the result, just we will get this diagonal matrix m times, but not the other ones. P and P inverse will just multiply before and after. Note that if D is equal to diagonal lambda 1, lambda 2, so on lambda 3, then D power m is equal to diagonal lambda 1 power m, lambda 2 power m, lambda 3 power m, and so on. Example Next example is that find the diagonal matrix whose diagonal entries are the eigenvalues of matrix A such that A is equal to 4, 1, minus 2, 2, 3, minus 1, minus 2, 1, 5. So first finding eigenvalues and eigenvectors of the matrix A. So we have to construct a matrix A minus lambda I. finding eigenvalues and eigenvectors of the matrix A. So A minus lambda I is the matrix 4 minus lambda 1 minus 2 2 3 minus lambda minus 1 minus 2 1 5 minus lambda A minus lambda I. So we will evaluate the determinant and we will get this 4 minus lambda into lambda square minus 8 lambda plus 10 equals 0. Lambda 1 is equal to 1.5505, lambda 2 is equal to 4, lambda 3 equal to 6.4495. And then corresponding eigenvectors are as follows. So first of all, we will find the eigenvalues and corresponding eigenvectors. So here, corresponding the eigenvalues and eigenvectors are already given. Corresponding eigenvectors are as follows: 1.2249 minus 1, 1, 1.5, 1, and minus 1.2247 minus 1 and 5, 1. Normalizing above vectors gives, so we can normalize this matrix, get the magnitude 1 square plus 1 square 2 plus 1.2249 square, then add these values and divide 1.2249 over this magnitude. You will get 0.3798 minus 0.3101, and then you normalize this one is 1 square 1, 2 square 4, 4 plus 1 5, and this 1.5 square will be equal to 6.5. So normalize this matrix, you will get this one, and normalizing the in the similar way, 1 square plus 1 square, so 2 plus this one, so you will normalize this third vector in the same way. Matrix P is constructed as just replacing this eigenvectors as a column of the matrix. So first eigenvector is 0.3798 minus 0.3101, 0.3101, and just put as a take as a column, first column, and then 0.2308, 0.3078, 0.1538. So second as a column, this one, and then a third one, this one. So you will get again this matrix P is equal to 0.398, 0.2308. Then you have to take the inverse of this matrix P. So after taking inverse of this matrix, you will get this P inverse is equal to 1.31648 minus 1.1958, 0.41691. So now just multiply matrix A with matrix P. So if you multiply this matrix, you will get this AP. Okay. And now you have to calculate this P inverse AP. It means you have to multiply this matrix P inverse with this matrix. Okay. So multiplying this one, P inverse AP, you will get this matrix 1.5505, 0.000263, 0.4 times 0, 4266, and here you see you have get this diagonal values, this 1.554, 6.44944875. Observe the diagonal of the matrix D contains eigenvalues of matrix A. So eigenvalues of this matrix A, this one, uh, this matrix. Before this, we have found all eigenvalues of this matrix, and here you have seen that all eigenvalues of this matrix are on the diagonal of the matrix P inverse AP. This one, 1.5505, 4, and 6.44944. 9, 4, 8, 9, 7, 4. Observe the diagonal of the matrix D contains eigenvalues of matrix A. So next example is find the diagonal matrix whose diagonal entries are the eigenvalues of A such that find the diagonal matrix whose diagonal entries are the eigenvalues. So here is the matrix provided that eigenvectors are k into 0, 1, 0 transpose, k into minus 1, 0, 1 transpose, and 1, 0, 1 transpose matrix P is constructed as. So it's not necessary to multiply with k. It's we can consider it as a mistake. So just these eigenvectors are 0, 1, 0, and this minus 1, 0, 1, 1, 0, 1. So construct the matrix P. You can also construct it without normalizing these vectors, but you can normalize. It depends on you. So the first column is 0, 1, 0. Second column is minus 1, 0, 1. Third column is 1, 0, 1. And then just take the inverse of this matrix. You will get P inverse is equal to 0, 1, 0, 0, 1, 0, minus 1, 0, 1. So then minus 1 by 2, 0, 1 by 2. Matrix P inverse can be found as, so how you can construct this P inverse? You can just take cofactors, matrix of cofactors. So then take a transpose adjoint of P is the adjoint of P is the transpose of matrix of cofactors which see A11 equal to 0, A11 equal to 0, A12 is equal to minus 1, minus 1, A13 is equal to 1, A21 equal to 2, A22 0, A23 0, A31 0, A32 1, A33 1. And the determinant of P is 2. So here is the adjoint of P, and then you have to take the transpose of adjoint of P. So taking transpose, you will get this 0, 2, 0, minus 1, 0, 1, and 1, 0, 1. Then P inverse is actually the adjoint of P transpose divided by determinant of P, and you will get this 0, 1, 0, minus half, 0, 1 by 2, half by. So in this way, you have gotten actually this P inverse matrix. Okay. Now multiply matrix A with P and you will get this matrix. And then multiplying P inverse with this matrix, you will get this matrix with whose diagonal contain all eigenvalue minus 2, 4, 6 of the this original matrix. Okay, so next is the vector norms. The set of all n-dimensional column vectors with real number components is denoted by Rn. The set of all n-dimensional column vectors with real number components is denoted by Rn. Notation norm is used to define a distance in Rn. So vector norm is actually the set of all n-dimensional column vectors with real number components, which is denoted by Rn. Notation norm is used to define a distance in Rn. Norm is the generalization of the absolute value on set of real numbers denoted by R. So definition, a vector norm on Rn is a function from Rn into R with the following properties. Number one, the norm of x is always positive. Norm of x is always positive. You see, the norm of x greater than or equal to 0 for all x belong to Rn. And norm of x, if norm of x is equal to 0, it is possible if and only if x is equal to 0. So if the vector is 0, so then the norm of the vector is 0. And the third property is that if we multiply norm of x with a scalar that is real number, okay, then we can write this real number outside of the norm. So we can say that alpha is act as a scalar or operator. And the third property is that the norm of x plus y is less than or equal to norm of x plus norm of y for all x, y belong to R. Okay. So here is an example how we can just compute the norm. For example, for the vector x is equal to x1, x2, x3, so on, xn transpose, L2 norm is defined as x norm subscript 2 is equal to summation I is equal to 1 to n xi square whole 1 by 2. If x is equal to minus 1, 1, minus 2 transpose, then x norm 2 is equal to minus 1 square plus 1 square plus minus 2 square is equal to 6 square root. And next example is for the vector x is equal to x1, x2, x3, so on, xn transpose. Infinite norm, L-infinite norm is defined as x infinite maximum of maximum I is equal to 1 to n, okay, xi. If x is equal to minus 1, 1 and minus 2 transpose, then x infinite norm will be maximum minus 1 absolute, minus 2 absolute is equal to 2. Okay. So next is the distance between vectors in Rn. Actually, norm of a vector provides a measure for the distance between an arbitrary vector and the zero vector, just like the absolute value of a real number describes its uh, distance from zero. In a similar way, the distance between two vectors is defined as the norm of the difference between the vectors, like distance between two real numbers is the absolute value of the difference between them. Therefore, for two vectors, x is equal to x1, x2, so on, xn, and y is equal to y1, y2, y3, so on, yn, then L2 and L finite distance between x and y can be defined as x minus y norm 2 is equal to summation I is equal to 1 to n xi minus yi, okay, 2, 1 by 2. X minus y norm infinite is equal to max I lies between 1 and n xi minus yi absolute value. So here is an example the linear system 3.3330x1 plus 15920x2 minus 10.333x3 is equal to 15913, and the second one is 2.2220x1 plus 16.710x2 plus 9.6120x3 is equal to 28.544. Next is the 1.5611x1 plus 5.1791x2 plus 1.6852x3 is equal to 8.4254. As the exact solution, x is equal to x1, x2, x3, so on x3 transpose is equal to 111 transpose. And if y is equal to y1, y2, y3 transpose is equal to 1.200, 0.9991, 0.9253 transpose, then x minus y norm 2 is equal to 1 minus 1.2002 plus 1 minus 0.999 4 times 91 plus 1 minus 0.925382, and taking square root we will get this 0.21358. Similarly, if we can compute x minus y infinite norm, we will get this 1 minus 1.2001, that we are actually subtracting the components. So the first component is 1, and here is the first component is 1.2001. So 1 minus 1.2001, 1 minus 0.9991, this one, and 1 minus 0.9253. So here we will get this, the distance between two vectors, distance between two vectors is 0.2001. Okay, similarly we can define this matrix norms as a matrix norm on the set of all n cross n matrices is a real valued function. Okay, so a matrix is a real valued function. If A and B are two square matrices, then matrix norm holds the following properties. Matrix norm is always positive, and matrix norm equal to 0 if and only if